All right, good morning, everyone. So this was meant to review one of the properties that we're going to be using today, and I'm not sure how familiar you are with it. It's a little bit tricky because when you look at this, you kind of think, well, yeah, the left side is the right side, right? They're both exactly equal, so whatever goes in for x is going to be the same. And that's the idea that I want to show you here. So let's say that I want to take the left side and change the left side into exponential form. So I'm going to take my base, which is 7, and I'm going to raise it to the power of the answer, right? So 7 to the log of 7 of x is equal to whatever the original log was, which is x. But we then basically had a property that said the logs are always going to produce, if you have the log of x base 7, it's going to equal itself. So whatever goes in for x is equal to itself, which means the log base 7 and 7, those are going to reduce out, and you're left with x equals x. Basically, whatever goes into the function comes out of the function, and it's the identity, basically. It's the same thing. So here we basically have the exact same setup. I've got log of x base 10. And if I change this to the base 10 and then raise it to the power of the right side, that has to equal whatever we took the log of. And then the log base 10, you can always write a 10 there, those reduce out, and we get x equals x. So the idea here is if you were to have a problem that just looked like this, a little side note, but let's say I told you to take the eighth power of the log of base 8 and it's equal to 15, right? We know that this log of 8, uh, base 8, and the eighth power, those reduce out, and the answer is just 15. And the whole reason why is the setup that we have here. Okay, so I don't need that. This is basically the same thing, except for when it is the natural log, we can change this. The natural log is really the log with base e. And then if I do the same thing, if I keep the base the same, and then I raise it to the power of the answer, hold on one second, I'm just marking attendance. That's going to equal whatever the original log of that was, so x. Well, then the e and the log go away, so x is equal to x. So basically, when you see the same base and the power of the log of that base, they reduce out. And that's the general rule, is that the general rule came from, we wrote this down the other day, it came from this whole piece that if I take the log, if I take the base b to the power of log of the same base, if those bases are equal, then they're going to reduce out, and the answer is x. So that's going to come up today. And we just need you to be aware of that and ready for that to kind of use it whenever it comes up. Okay, before we get going, I'm just going to let you guys know we're going to do some Zoom chats. We're going to do a breakout room. I'm looking to measure your level of engagement and see who's participating and who's just logging in for attendance. And then I will use that data to contact parents if I need to. All right, really quick, you do not have to write this down, but I want you to send me a private chat. What do you notice and what do you wonder about the two different functions? Okay, and I'm going to read them out loud as you guys just throw a chat in there. But the red one is the log function, you can see that here, and the blue one is the natural log function. So throw it in the chat. What do you notice? What do you wonder about the two different functions? They both start at the same point but move differently. Nice, Lauren. The blue one is much higher than the red one. Yep. They intersect at one point. The natural log function is larger than the log function. Okay, the natural log function goes higher on the graph. They cross both in the same shape. Why is the log one lower? Right? These are great questions. In x runs higher along the graph, or the natural log of x, sorry, runs higher along the graph. Both are going to the right. They're different shapes or different slopes. They both have the kind of the same starting point, but one gets larger. They have the same intercept, very similar. Okay, one stops at a point. The red line goes closer to the y-axis. Y goes higher. The natural log of x is larger. It looks like they kind of have similar shapes to a parabola, but tilted. They don't go past y equals 0. Jade, you nailed it. That's exactly what I was kind of going for. And all of these are great. The red one is a lower function. It gets closer to 0. Nice. Starting points are the same. Now we got a graph. And are there asymptotes? These are wonderful things, and you guys nailed it right on the head. And that's what I want to show you really quick. Is the log and the natural log are very similar features. The only difference is the natural log grows faster, and you can tell because it has higher outputs than the log. So the log is a slower growing function, but notice as we go to the right, they're both going to be going up towards positive infinity. So their outputs are going to keep growing and growing forever. But the big thing was what Jade mentioned. And I think that's a very important concept right here that we need to take in part here is notice they will never cross the y equals 0 line, right? Which means both of these functions, their outputs, or I should say their range, for both of them is y has to be greater than 0. Which means I cannot have any negative values. So think of this. If you have the natural log of a negative number, it does not exist. If you have the log of a negative number, it does not exist. And that is going to come up today. We're going to actually solve these, right? So we're going to be looking at how do we solve functions that involve log and natural log. And then we're going to get answers. And when you check your answer, whatever is in between the parentheses here has to be a positive number. When it's all simplified, whatever's in between has to be positive because the y value is always greater than 0, which means we can never take the log of a negative x. Notice how my, actually, you know what? I wrote this wrong. This is not the range. Sorry. I was just thinking it's the inputs that can't be negative. The y values, actually, the range is all real numbers. It's the domain that x has to be greater than 0. The range is actually all real numbers because we go forever down and forever up. So I accidentally miswrote that, which means your inputs, notice we don't have any x values here that are negative. So all the inputs, when you take the natural log or log, have to be positive. All right, and that's the big thing. We are not going to be officially graphing these, but they are graphs that you're expected to kind of know. And you can see they're just very slow growing functions. Okay, another point, this is more calculus related, but it's a big, big idea that we use often. Notice the exact same point. They share, and a lot of you identified this, they share the point when x is 1, y is 0. Right? So that's a very common point. The log of 1 is 0, and the natural log of 1 is 0. And we actually explored that when we did the change from log to exponential form, because anything to the 0 power is 1. And that's the idea that this is introducing. All right, Really quick, I would like you guys to look at your grade book. I want you to open up Schoology and or Campus. If you go to Campus, you'll see what's officially missing. If you check your Schoology gradebook, you'll see any comments that I may have written on an assignment. But I just, as of maybe a half hour ago, I just updated grades. And anybody that did not take the quiz on Wednesday, it now is marked as a missing. If you have any homework that's missing, that needs to be submitted. Um, and there's one other thing that I just got to mention because this happened with a lot of people. I had probably gotten 5 or 6 emails that said, "Hey, Straub, I finished all the Delta math." So I went into Schoology to check, and those Delta maths were not submitted. And that's the other thing is you have to submit your screenshots to Schoology, otherwise I won't know to go in and look for that. Okay. Now, what I did, because a lot of people did that, and I was already checking it, I actually, if you didn't submit it, I actually did update your grade, but I'm not going to do that every time because that took a long time for me to go find each individual person and go in and update their grade. So I just want you to be sure that if you do finish a Delta Math assignment, you're taking a screenshot and you're submitting it to Schoology. Okay? And the other thing I want you to know is all of this work is the last chance to turn it in is next week, Friday. And that's what I want to show you here. So right now we're on Friday. And this is, think of this block as your Monday, Tuesday. Here's your Wednesday, Thursday, Friday, depending on what day we see each other. So today we're doing 3.5. Next week, we're going to do more with 3.5 and solving exponential equations. But today we're solving logs. And then we've got a review. And then our test is next week, Thursday. I'll see you guys on Thursday. All the late work for this unit is due, including quizzes, is due by December 17th. Okay, no exceptions. After that, I'm going to turn them into zeros, and you will not be able to work on them after that. All right. Now, what that means is you then don't have any homework over break. And when you come back from break, you don't have any late stuff to work on. You're 100% caught up. Hopefully, you're going to get that stuff done. Okay. So we're going to jump into 3.5, and I'll just copy this. Maybe I won't. I'll just write it. So this is section 3.5, and we're going to look at solving logarithmic equations. So we talked about all these properties of logs, but we've never once talked about how do we solve them. And that's the goal today, is we're going to equip you with the skills that you need. Now, some people like kind of a step-by-step, here's what you should do. I personally don't think you need to write all this, but we're going to look at 2 different ways to solve a logarithmic function. The first one is to change the equation from log form to exponential form, and that's kind of what we did in the warm-up, because we actually know how to solve exponential equations. We've done that before, but we've never solved log equations. The other method we're going to look at is exponentiate both sides. And I actually personally like the second method the best. I'll show you both, and then you get to decide which method kind of works best for you. And to be honest, it depends on the problem, which one is easiest. But I put little asterisks here because I do want you to remember a couple of skills that are going to come up. So we want to remember to isolate or condense the log expression first. So if there's a lot of log pieces, we can condense them into one logarithmic expression and then solve. And that's where those properties over the last couple days came from. Then the other part is we always want to check our answers. When we get answers, we need to plug them back into an expression and just confirm that they're going to produce an actual true result. A quick way to do that is what we just explored on that graph. And that's what I have here in green. If you're checking an answer and you have the log of a negative number or the natural log of a negative number, we know those values don't exist. So if whatever you're plugging into the parentheses is a negative output, that means that this cannot be true. It's not going to work. So that's a quick way for us to check for extraneous solutions. And remember, extraneous solutions are solutions that appear, but they produce a false result. So I'm going to give you a minute to. Okay. So first method we're going to use is to change from log to exponential. So notice we have my base. My base is 4. And then I have the answer. If I take the base to the power of the answer, that has to equal whatever we're taking the log of. So in log form, I don't know this answer and I really don't know how to approach it. But if I change it to exponential, well, now you can just kind of quickly grab your calculator and do 4 to the 5th power, and we'll get x equals 1024. Really quick. All right? That's the way that I prefer when I see problems written in this method. All right? Let's look at the other option. And this one's a little bit trickier, and some students really like it. But however you want to think of it, what you can do is we're going to exponentiate both sides. Well, the way to do that is to change this so they're both in the same exponent. So notice I have a base of 4. If I raise both sides to the power of 4, or I should say, if I raise 4 to the power of both sides, that's not changing the value of the equation because we're doing the same thing to the left and the right. But what it does do is it takes that warm-up that we just talked about. If I have the log of 4 in the exponent, so 4 to the power of log of 4, those reduce out. What's left over is 4 to the 5th power, which we know is 1024. So it's very similar. I personally like the first method because it's less work. Right? So let's look at the next one and kind of do this 2 ways again, just so you get an idea of it. I've got the log of x equals -5. Well, we have to be careful because in this case, the base isn't written, which means there always is a base 10. All right, so now we're going to do method 1, is we're going to change from log form to exponential. So I'm going to take the base of 10, raise it to the power of the answer, and that has to equal whatever we were taking the log of originally. Now, this one I would expect you to do without a calculator, and the reason why is because the negative. You should know that the negative goes into the denominator, and then if I have 10 to the 5th power, that's just a 1 with 5 zeros. So we don't need a calculator for that, and we don't really want decimal answers, by the way. It's kind of why I don't want you to grab your calculator all the time. Okay, what's the second way of doing this? It's taking the original expression and it's raising both sides to the power of the base. So just take, and we just call it exponentiating both sides. So whatever the base was, it's 10 to the power of that. And then we know from the warm-up that the 10 and the log 10 go away. And I'm left with the exact same answer. Okay. You will not have to show both ways. You only really have to show the way that you prefer. Okay. So what about a problem like this? Notice the difference between these two problems. Here, In the first two problems, x, we're taking the log of x, and that's what we wanted to find. And x ended up, if I switched it, x was the answer. But how do we do it if x is the original answer and I still need to find out what is the log of 64 base 4? And we can't, right now, we don't know how to do this in our calculator. Because if you use your calculator, we've got a base 4 that we really don't know about. I don't know how to enter that into my calculator yet. So, what we need to do, and this is, I think, this is the only method one really helps us here, is we're going to do the change of form. We're going to go from log form to exponential. So 4 to the x is equal to 64. And then you have a couple options. Okay, now I have to figure out what x, 4 to what power, gives me 64. Well, what we could do is we could break 64 down. And just look at another way of writing 64 is 4 to the third power. And then anytime you have the same base and they're equal, the bases are going to basically go away, and you're left with x equals 3. All right, so I do want to note one thing. I just solved 3 different problems. And one of them, x was the original answer. The other ones, x was part of the log. So here, this is just an answer. And once I teach you how to do this on your calculator, which we're not going to do today, you'll be able to confirm this very quickly. But the first two, if I plug this answer back in, notice this will work. And the only way we can kind of confirm that it is not an extraneous solution is x is a positive number going back in. So that is going to produce a true result. And 1 over 10,000 is also a positive number, and that's going to produce a true result. Okay. All right, I'm going to have you guys do 2 problems, and I want you to send me a private chat with your answers. So all you have to do in the chat is say, number 1, x is equal to this. Number 2, x is equal to this. And then just send that as a private chat. Make sure you don't respond all, because I want everybody to try this. And we'll go about, so I'm going to, once we really get into this, I'm going to focus on the method that I think is the easiest and the least amount of work. And what I would do here is I would change this from log form to exponential. So we're going to take the base and raise it to the power of the answer, and that has to equal 256. And then we're looking at, how do I solve exponential problems? Well, we know how to get rid of a square root. So you can do the 8th root, or let's say you forgot how to do that in your calculator. There's 2 ways that you can do this, and both of these are equivalent. The 8th root is actually the exact same thing as raising both sides to the 1/8 power. So if you know how to do the 8th root in your calculator, I'll show you that. If not, you can still do it to the 1/8 power, because the reason why this works is 8 times 1/8 is 1, so that leaves me with x. And then we just have to take 256 to the 1/8 power. I'm going to pull up my calculator here quick and just show you how I would do that. Okay. So if I'm going to do the first method, I have to type in 8, and then I have to go to math. And option 5 is the x root. But notice that x has to have an input. So I had to put the 8 there first. And then we'll select the option 5. And we end up with 2. And notice if I do 256, ooh, 256 to the 1/8 power, I will get the exact same thing. So two ways to solve that. Both ways you get 2. So nice job. Everybody, I think almost everybody had that, which is awesome. And this one, super quick. You might even know the answer without even doing any work, right? We have the base of 9 raised to the power of the answer is equal to x. And in that case, x equals 81, 9 squared. Okay. All right, let's look at another concept here. So look at this, and that's the goal here is the problems are going to look a little more challenging. Our goal is to make them simplified so they're easier to deal with. Okay. Now, our hint, just like anytime we have algebra, we want to isolate certain pieces first. So I need to isolate the log portion first, which means I just have to move everything over to one side. Okay. Now, one thing to think of is anything that's being added, subtracted has to move over first. This is the reverse of PEMDAS, right? We have to, some people like to draw the line here. You don't need to show this work to start, but I want to move the 1 over first. So that's equal to 1. And then I have to deal with the 1/2, right? That 1/2 has to move over to the other side as well. Well, to get rid of a 1/2, we times by the reciprocal, which is just 2. And now we have the log isolated. Now this one also is a little bit different because it's not just x. We've got x plus 7. Notice that x plus 7 is in parentheses. That is protected, and I can't do anything with the x plus 7 until I move the log or get rid of the log. So we're going to take that same approach now, and we're going to change this from the log form into exponential form. So I'm going to take 10 to the answer, 10 to the power of the answer, is equal to whatever is in the parentheses. And now it's just simplify. We know what 10 squared is. And then just subtract. I'm not going to do this for every problem, but what were the steps that we just did in this problem? This is basically, if you are an avid student, I'm going through and annotating my notes right now, right? Taking the steps and just explaining what did I do. And this is a great way to study for a math class is if we ever do a problem in class and you want to study it more, write out the steps next to it on what we did. Well, I can't spell simplify. There we go. All right. So the green part is basically the steps that we did. The last thing is once we get at our answer, we should just kind of check this answer really quickly. Now, we don't know how to enter this into our calculator yet, but the one thing I can do is say, what if I put 93 back in for x? 93 plus 7 is a positive number. And since that's a positive number, it's going to produce a real result. And for right now, that's all we're good with that. Okay. On next week, Monday, I'm gonna show you guys how to check this in your calculator, but we're not gonna do it today. Otherwise, that would really eliminate a lot of work. Okay. So you don't have to annotate, but that's the steps that we did. Let's try a couple more, and then I'm gonna have you guys do another one where you submit your answers. So notice what's going on here. We got a lot of stuff going on, right? I've got three different log functions. One of the first things I just want you to be aware of is that they all have the exact same base. You cannot combine log pieces together if they don't have the same base. And we're not going to try to trick you right now. Every delta math problem I've checked out, anytime you have a problem, it's always the same base. So that way you don't have to kind of be super aware. But what we need to do is I have too many things with logs going on right now. I want to make them condensed. And that's the first thing we're going to do here. We're going to condense the right side first. And this is our properties from the other day. When we had addition, right? That addition of two separate logs, we could rewrite as the multiplication of 1. Okay, so hopefully you're comfortable with this. The log of the first one times the log of the second, or times the second, is just 5x to the third. And then I've got log of 10 4x. Now, there's a couple of things. We could make this a lot longer and try to move this one over here with subtraction and then end up dividing, and it'd be equal to 0. But in this case, it's actually better to exponentiate. So notice they both have a log of 10. Now, logically, if these are equal, then whatever's inside of the parentheses have to be equal, right? But how do we show that? Mathematically, I skipped a big step here. So I just want to show the exponentiate. They're both logs of base 10. So if I raise both sides to the power of 10, or I should say 10 to the power of both sides, that is what officially reduces out the log of base 10, right? That was what we saw in the warm-up today. So now what's left over is just 4x, and since I'm going to have to do this anyways, I'm going to just distribute at the same time. And now it's just algebra. Real quick algebra. I don't care how you solve it. Subtract a 5 over to one side, 5x, and then divide by -1, and x equals 15. But let's do a mental check, right? If I have 15 and I plug it in for 4 times 15, that's a positive number. I'm okay with that. If I plug in 15 here, 15 minus 3 is a positive number. There isn't any concern about this answer. So as of right now, we're just going to trust that it works until we show you how to do this on your calculator. All right, let's look at the next one. You can see we've got log base 3 plus log base 3. Both of the bases are the same, which is key. And then I have to use my condensed part first. I want both of these logs to be written as one expression, and then it turns into the same problem we just did on the last slide. So condense first. And we just have the addition. So we're going to rewrite this as the log base 3 of 5x times 5 equals 3. And if you can do that in your head, you can write 25x to save an extra step. Okay. I'm just showing basically all my steps in case somebody is looking back at these notes later on. So now, this is just a problem where we can do our change of base. You could exponentiate both sides and raise this to the third and raise both sides 3 to the power of each side. I don't like that for me. Personally, I like to take the base of 3, raise it to the power of 3, and that equals 25x. So I changed from log form to exponential. And then it's just simplify. We're not going to get a super friendly answer here, but that's okay. Right? 3 to the third power is 27. Divide both sides by 25. And there's my answer. Now, I do know that that's a positive number, right? It's just bigger than 1. It's a positive number, and if I plug that in for x here, that's going to give me another positive number, which doesn't raise any red flags. So that is a true answer for right now. We'll show you how to confirm that next week. All right, I'm going to have you try another problem, and I want you to chat me the answer. The only hint I'm going to give you is take a look at this one. So first thing we have to do is condense, right? And we have to deal with that subtraction piece first. So when we have subtraction of two logs with the same base, we can rewrite that, keeping the log of the same base, but then we divide. So there's your first step, right? When you see subtraction, think it's really rewritten as the division. And then what I would do, they don't do this in delta math, and I'm trying to figure out the reason why, but 9x divided by 3 is just 3x. Simplify that, right? So if I simplify that, that makes it easier inside. And now I'm going to take the base of 7 and change it from log form to exponential. And we get 7 squared, which is 49, equals 3x. And then 49 doesn't go into 3x evenly, so I would just stop right there. Okay. Now we do have to check mentally, right? 49 divided by 3 is going to be a positive number. When I plug that in, I get 9 times a positive number, which is positive, and everything else doesn't raise any red flags, so we're going to say that that's okay. which I know isn't the best way for me to describe that and how we check, but we don't have our calculators yet to be able to use this. So right now we just have to check for if it's a negative number overall, then that raises a red flag. All right, we got a couple more to look at. This one is really interesting. Okay. So I'll give you a second to write this one down, but notice there's something a little different here. We've got the log base 15 of x plus 30 equals 3 minus the log base 15 of x. But this 3, I can't combine the 3 with a minus log of x base 15. I can't combine these or condense them together. So I have to basically find another way to help me isolate the logs. All right, so first thing is I need to move this log over to the other side to help me condense. So I'm just going to add log of 15x over to the other side. And you don't have to show that actual addition moving over. But I'm just going to add the log of 15 over to this side. So then 3 is by itself. And now this turns into basically the same problem we just had, except for the algebra is different, and which is why I want to show this problem and do it together. So now I have to deal with the fact that I have two logs being added together. And when I have two logs being added together, we can condense. So I'm going to do the log of 15, and we got to remember, what does addition mean? Addition tells us to multiply, right? So I'm going to do x plus 30 times x. I might write that in a different color so it just appears better. Which you can distribute here. I'm going to do that in a second. But then the third thing, now we're just going to change forms. We're going to go from log to exponential. So 15 to the power of the answer has to equal x plus 30 times x, but let's go ahead and actually distribute that.
Where did 15 to the third come from?
We changed it from log form to exponential. So the 15 stays the base, and then to switch from log to exponential, we take 15 to the power of the answer. So that's where this 3 was the answer, and 15 remains the base. Okay, so now this is where we're going to need our calculator a little bit. I need to just figure out what is 15 to the third power, and that's a pretty big number. It's 3,375. Right? So I'm going to move that over to the other side with subtraction. And then comes the fun part. You have a couple of options. It's a quadratic. You could use the quadratic formula. That will work every single time. Or this one actually is factorable. And you do not have to draw the box for this one. And I don't want to spend a ton of time trying to find the factors, so I'm just going to actually give them to you. So I'm looking for the factors of negative 3,375 that add up to 30. And I'll just let you know, 75 times 45 is what gave me 3,375. And then one has to be negative, but I need a positive 30x when we add them together. So the smaller one's going to be negative. And you don't even need to show this box, right? I'm just kind of reviewing it because that's what you would do if you didn't really know the factors. But then we can quickly factor the common factors from each piece. So hopefully you're super comfortable on factoring. But do notice that when we factor and we do all this work, we get two answers, right? We get the zero product property, we set each factor equal to its own zero, and then solve. And here's where students usually stop. And we got to warn you about that. We're not technically happy with our answers until we just confirm that they both work. They could both work, one could work, or potentially both be extraneous solutions, which would be kind of rare, but I guess that could happen. So I'm going to take a look at 45. What if I plug 45 back in anywhere I see an X? Does that raise any red flags? Nope. Positive 45 plus 30, that's a number, that's 75. That's a positive, we're good there. And if I plug in 45 here, that's a positive number. So I'm good with 45. But if I plug negative 75 in here, negative 75 plus 30 is a negative 45. Right there is a concern, as well as just plugging negative 75 in here. We can't have our x value be the whatever it's simplified, you can't have the parentheses be negative. So that's where I would cross this out and write it's an extraneous solution. If I was to plug that in and check it with my calculator, it would say error. Okay. So I just wanted to show this problem because the algebra isn't always going to be quick and friendly. But we know how to factor, and the expectations are you're going to remember how to factor or potentially use quadratic formula. Okay, what about these problems? Natural log. I'm going to show you the real quick way to solve this. There are multiple different ways. Delta Math does this a little differently than I do, but I prefer this method to anything else. We know at the start of this unit that the equation y equals e to the x, and if I converted this, the natural log of y equals x, these are inverse functions of one another, right? The e and the ln kind of reduce each other out. So, knowing that, one way to get rid of this natural log is to raise both sides to the power of e. Which, what happens is the natural log and base e go away. And then my answer is e to the power of 6. Now remember, e is a number. It's 2.718, so, and it continues on. But we want to just leave our answer in this form. Right? I believe Delta Math solves this problem this way. And you don't have to write this, I just want to show it to you. Mumu, I just got your response. I changed it as soon as you logged in. You're good. Okay, so here's how Delta Math solves this. Sorry, a couple people are responding. If you joined late, I had marked you absent, and then as soon as you logged in, I changed it back so you are not, if you're present in class right now, you are not marked absent. But you just got that notification that you were. So, okay, let me quick talk about delta math. Delta math says the natural log of x can be rewritten as the log base e. And then we can go ahead and do the change of base or change forms. So I can take the e to the power of the answer, and that equals whatever we were taking the log of. So notice this is a lot longer. I really prefer this way because the e and ln are inverses and they'll undo each other. Okay, so let's look at this problem here. If I want to undo the natural log, notice it's isolated. This is basically protected in parentheses. So I'm going to just raise both sides to the power of e. The natural log and e go away. And we aren't going to do anything with our calculator. We're just going to call that e to the 8th power. All right? Now, the question is, what do I do to get rid of a square root? Well, we square both sides. And when I square both sides, the square root and squared go away. And then this is a power to a power, so we multiply the exponents. And then it's just a one step to solve. Bring the 8 over, and we can't, and we don't want to, get a decimal answer. We just want to leave our answer as e to the power of 16 minus 8. And then I do want to confirm e is a positive number, and a positive number raised to a positive power. E is always going to give you a positive answer. So checking these will always be positive answers going in, which means our answer right now we're happy with. It doesn't quickly identify if they're extraneous. All right, I got one more slide for us to go through. And this last slide it can be tricky, so just really pay attention. And we're going to do these fairly quick. We have to be careful when we have negatives as answers, right? Or if there's a base, any negative that appears, we just want to be cautious of that. So watch what happens here. I've got the log of 1 over 81, or 1/81st. Base x is equal to -2. Well, let's do that change of base, or excuse me, change from log form to exponential form. All right. Now, a lot of students kind of get confused. What do I do with the negative? And there's many ways to solve this. I want to show you one of them. And this might be a little bit longer, but what I've found, and my calculus kids struggle with this, so I show it this way. What do we have? We have x to the -2nd power. Well, that's the same thing. If it's a negative, that's the same thing as putting 1 over x squared, and it's equal to 81. So you can then cross multiply. 1 times 81 is 81. X squared times 1 is x squared. And then I'm going to take the square root of both sides. And I get x equals -9 and x equals +9. Because whenever you take the square root, remember, you get two answers, plus or minus. Now, we have one small problem. Our base should always be positive. And there's a reason why. I'll show you on Monday why that works. So in this case, we only have one true answer. Did not come out the way I wanted to. X equals -9 is an extraneous solution. X equals +9 is the only value that works. All right, last one. Actually, I take that back. Second to last one. This one will go fairly quick. So we're going to do that change of base again. We're going to take the 10 as my base, and I'm going to raise it to the -3rd power, and that's equal to x. And here we don't need any crazy solving pieces. We just need to remember the -3 brings this down in the denominator, and 10 to the 3rd power is a 1 with 3 zeros. It's a positive number, so no worries. Okay. Last one, I wanted to make sure we got to this one too. Okay, so I am going to change the base here. I'm going to change it as x to the -2/3 power is equal to 1/9. Okay? Now, this scares a lot of kids, and there's more than one way to solve this. I'm going to take the same approach we did with the first problem. I'm going to use that negative and rewrite it to the 2/3 power, and then set up cross multiplying. Right? Because 1 times 9 is 9, 1 times x to the 2/3, and then I have to think of how do I get rid of the 2/3 power? We raise it to the reciprocal. So good review of Algebra 1 skills right here. This becomes 6/6, which reduces down to x to the 1st power. And then I've got 9 to the 3/2, but we've seen this before. And we said if it's 9 to the 3/2, you can actually take the divide by 2 and call that a square root, and then do the 3rd power. Or you could do the 3rd power and then the square root. Either one will work. I think this is the fastest route. Why? Because I know what the square root of 9 is. The square root of 9 is 3, and 3 to the 3rd power is 27. And 27 is a positive number. That's not going to raise any red flags here, so we're happy with that. Okay, so your homework tonight walks through all of these problems. My advice, and I really hope you take it, is to show your work, show all your steps, because those are the skills you're going to need to be successful next year in calculus. All right, I'm going to post this video and the notes worked out. So if you missed anything, you can always go back.